So this is another class of cutting planes called perspective cuts. And I'll show you that they can be very powerful. So many mixed integer nonlinear optimization problems use binary variables basically for one reason: to switch on and off constraints and to turn variables on and off. And so we've seen this structure before, this variable upper bound constraint, where a variable x is either, or a set of variables x is either 0, if y, the indicator variable, is 0, or they're free to be between 0 and some upper bound if y is 1. And the perspective formulation that we're going to study here, that applies when y is also somehow involved in this convex function that we have that has some upper bound. And this was actually, you can then significantly improve the formulation, and that was popularized by Frangioni and Gentile in 2006. Okay, so we've seen this picture before and this particular set. So this is one particular set that's illustrated down here in the picture. So let's take this apart a little bit. There are two continuous variables, x1 and x2, and x3 is a binary variable. And x3 basically switches x1 on and off. So if x3 is 0, then x1 is 0, and otherwise it's free to be whatever it wants to be. And x2 is just, you can think of this as your objective variable, for example. It's just above x1 squared, if that were the cost. And you can write this set as the union of two sets, S0 and S1. S0 corresponds to the case where I set the binary variable to 0. And if I set the binary variable x3 to 0, then x1 will be 0. And x2 is just anything that's above x1. And if I set the binary variable to 1 here, then x1 is allowed to vary between its lower and its upper bound. So the x3 is equal to 1 is over here at the back. And x2 is above this parabola here. So the feasible set then is this set that I have here with a lower and an upper bound, and it goes off to infinity there in terms of x2. Okay, so how can we derive convex formulations or cuts for these problems? And we've seen this before. What we want to do is we want to connect the origin and this parabola at x3 equal 1. So this was indicated here by these red lines. So what we want to do is we want to find the convex hull of these two sets by connecting this origin and these lines that are moving up here. So if we can do that, then we have the convex hull. And it turns out that in this case, the convex hull can be written equivalently as this set here. And you can check that. And this function, this function here is not necessarily convex because x2 times x3 is a bilinear term, but it's defined effectively in terms of this perspective function. So the perspective, that's a formal definition of a function f, evaluated at x and z, is either 0 if z is equal to 0, or it's this product of z times f of x divided by z. And so that's exactly what was written here. And for indicator functions, we can then write our inequality constraints in this form, and it gives us a tighter convex formulation. So this is very nice, and we can use that now, for example, to generate cuts. So there are two ways of using this. One is to reformulate the problem in this way, and the other one is to generate cuts. And Oktay Günlög and Jeff Lindroth figured out how to, in this one example, how to generate cuts, and they have a formula for a subgradient. So they looked at a set where they just have a single objective function that's nonlinear with a linear term, some linear constraints that are, and the right-hand side is bounded by z. The polyhedron is bounded, and f of 0 is 0. And so they showed that the subgradient, because this function is not necessarily everywhere differentiable, is then given by this inequality down here. And they've implemented this, and I've sort of borrowed those slides from Jeff. What he can show is that for a particular problem, in this case a separable quadratic facility location problem, you get much, much tighter bounds if you generate a few of these cuts. So there's the value of the nonlinear optimization relaxation, that's the value down here. This is for different sizes of problems with facilities and customers. This is a different formulation that gets a slightly better bound. The optimal solution or the optimal value is over here, and the solution that they generate, or the lower bound that they generate, is much, much closer to the optimal solution. So you get very tight lower bounds by generating a number of these cutting planes using this trick or using this formula for the hyperplane. Okay, so I'm also interested in nonlinear optimization, and one of the issues, of course, is that this perspective, the danger is that you have this division by 0. So if I just write the perspective of a nonlinear function h of x with this binary variable, that's my perspective, then if y is equal to 0, I will encounter a division by 0. And in fact, function gradients and Hessians may not be well defined. And if you look at a few examples, one of the things that's interesting is that the Hessian is actually more prone to having higher order terms of y in the denominator. There's a very simple problem that, again, people have looked at the stochastic service system design problem. And so this is a very simple, just a 3-dimensional problem. We have, there should be there's 2 continuous variables and 1 binary variable. So z is a continuous variable, v is a continuous variable, and y is the binary variable here. And the perspective of this constraint is you use this formula up here, and if you write this out, then you end up with this term over here. So what I did was, you just plug in the formula. The interesting part is that in this case, the linear terms just cancel out, but you're left with this term in the denominator. So that's not defined if y is equal to 0, even after cancellation. And so there have been a number of reformulations that people have studied, so of this formulation. So there's the original perspective formulation that's up here. You can simply multiply through by the denominator and rearrange terms, and then you get a smooth reformulation that looks much more appealing. And there's another formulation that's a second-order cone formulation. This second-order cone formulation, unfortunately, requires you a solver that may not be easy to warm start. But if you run your nonlinear solvers on the second formulation here, then you find that that also doesn't work very well. So this smooth formulation creates issues for the solvers, and it was long suspected that this was because they're non-convex. But that's actually not correct. The nonlinear optimization solvers fail because you can show that this formulation here violates a constraint qualification. And so the solvers will converge slowly there. And I'll give you an example in a moment. A branch and bound solver will also fail on this perspective formulation on any node for which you set this function equal to 0. So whenever you branch and expect your nonlinear solver to solve the problem, it will just complain that it cannot evaluate the function and throw an IEEE exception. So, but going back to this formulation up here, the smooth formulation, if I run this, and this is a slightly different problem that I was running here, it turns out that when you look at your solver, when you look at the output of the solver, it kind of makes good progress initially, but then you observe this slow linear rate of convergence. So the objective function is slowly converging to 0. The norm of the step is also linearly converging to 0. And there's a sort of hint here that not everything is good, in that the solver complains that the step got too small. And the slow convergence is really something that you will see whenever constraint qualifications, such as Mangasar and Fromowitz constraint qualifications, fail. I can actually show you real quick, I think, that in this case the constraint qualification fails. Let's see if we can do that real quick. So we have x squared minus zy less than or equal to 0, and x is between 0 and z. And z is a binary variable. Okay, so the first one I could try out is the linear independence constraint qualification. And so I would just write down the gradients that I get out of these constraints. So that's 2x. Then there's a minus y and a minus z. And then depending on which of these constraints are active, I will get two more. I will get a 1. So that looks okay, except at the point, sorry?
The last one should be 1 minus 1, 0, 1. Because x and z.
Oh yeah, x and z, sorry, yeah. There we go, yeah, that's right. Okay, thank you. Okay. And so if I converge to a solution, so if I, sorry.
It's actually minus 1, 1, 0. Last column.
Last inverted signs, the last column. 1, 0, minus 1.
No, 1, 1, 0.
Second
Minus 1, 1, 0. The second row is for
z.
Z variable.
Yeah.
Oh, it is, yes, sorry, I got this the wrong way around. Yeah. There we go. Okay. So if I now look at this at the origin, then this column is always 0. So that means I don't have full rank. And I'm not going to try to do this here on the fly, but you can also look at the origin, again, you will have 3 constraints that will be active, these 2 and this one, and there's no, you can show there's no directions pointing strictly into the interior then. And the reason is actually the presence of this bilinear term here. That's similar to complementarity constraints. Okay, so there's you can write a lot of different formulations, and you can reformulate them. So here's another reformulation. You just multiply through by the denominator. You get this formulation. Then rearrange the terms. We're here, and now you do a little trick where you add and subtract the square. So that doesn't actually change anything. That's completely equivalent. And then I can rearrange this inequality, put the square, one of the squares on the left-hand side, and what I have on the right-hand side can then be written as a rotated second-order cone. So this is a formulation that Pietro came up with or showed me. And so this is also cool that you can, the trick here is that you do the reformulation, you introduce the right kind of squares and subtract them in the right way so that you end up with something that looks like a rotated second-order cone. So again, you have these 2 variables over there. Okay, and then and the nice thing now is that you have this binary variable, which is if z is equal to 0, then x is equal to 0, and then y is less than or equal to 0. And so we can now replace the left-hand side here, the 1 by a z, and get an equivalent constraint. So if z is equal to 1, then the constraint is obviously equivalent, because z is equal to 1. If z is equal to 0, then we had, and that's missing here, the upper bound, then x will be 0, and the constraint just reduces to x squared less than or equal to x squared minus y, or y less than or equal to 0. And so for z equals 0, you get the same constraint here. Okay. Cool. So this was just a short summary of perspective formulations. They're tight and correspond to the convex hull of these feasible sets that are switched on and off. They suffer from the issue that when you divide by 0, you can't use our nonlinear solvers because you get IEEE exceptions. And the reformulations that you might try out also somehow fail because they then fail to violate constraint qualifications, and you get slow convergence. So the way then to use these perspective formulations is to either write them in a way that are second order cones and then use conic solvers, or to use cutting planes, to generate cutting planes from the perspective. And when you use the cutting planes from the perspectives, that's when you get really nice and strong relaxations. So the perspective formulation as such, for a nonlinear solver, it's not very useful, but as a tool for generating cutting planes, it is very useful. And so you almost want to keep this idea that use the perspective either as a second order cone reformulation or as a cut generator. And if you use it as a cut generator, then it's a very powerful tool, but don't use it for your nonlinear solvers. They will not work with this. Okay. So this was just a very short introduction. I'll have a bit more in the next lecture, I hope. But I'm also happy to answer questions or